Cool. Thanks everyone for coming. If you missed it, Domino's will be here at the end. And if you really, really prefer Chipotle, just let us know and we'll grab you one. And okay, so I wanted to get a little bit of like kind of feel for how the room is in terms of like what you understand and what you don't. So I know like what to skip over and what to spend more time on. So like maybe raise your hand if you like know what attention is. Okay, cool. Raise your hand if you know things about proteins and drug discovery. Okay, cool. And then raise your hand if you know what invariance or equivariance is. Perfect. Okay, this is exactly as I expected. Like, if you know what invariance or equivariance is. Okay, great. Cool. Okay, so I have a good sense of who knows what. And then people on Zoom, can you guys like hear me and see me good? You just want to like give like a little yes or thumbs up or something. Okay, cool. Awesome. Also, if you haven't checked in, QR code, it's a little cut off now, but great. Cool. So I'll start with a little bit of like kind of intuition and impact and why this is important, but I'm only going to spend a couple minutes on it because you guys are kind of more here for the little more technical detail. And so what was the impact and kind of what is the timeline? So I think to understand this, you have to kind of understand the history a little bit. So the CASP, Assessment of Protein Structure Prediction, it's a competition. They give you a bunch of new proteins that have never been seen before. You have to predict what their structure is. And this competition has been running for like 14 years or something like. And DeepMind won in 2018 and 2020, Alphafold 1 and then Alphafold 2. There was approximately a 2-year delay between winning the first one and releasing the paper to the second one, along with the full human proteome. And this kind of full human proteome is a pretty big deal. And part of that is because previously, or maybe the impact of this problem exactly is that once we predict the structure of the protein, there are some things that it gives us and something that it doesn't. So it doesn't give us what the functional information is. It doesn't tell us, okay, this protein is like doing this in this specific pathway. We generally already know from the sequence of the protein. And the most important proteins have already been, X-ray crystallography sequence, X-ray crystallography imaged, and we know exactly what the structure is. So the most important ones we kind of mostly knew. And the thing that this does enable is this kind of holy grail of drug discovery, which is like universal end-to-end molecular drug discovery pipeline. You stick in any protein and you get any molecule at the end that disables the protein. And that's kind of a lot of what the big pharmaceuticals are working towards, and that's a lot of what this enables. That you can just like plug in a random protein and figure out how to solve it. And that's basically like almost like a golden key to cure like a lot of different diseases, which is why this is such a big step forward. Cool. So what are the actual innovations in this paper? So I'm sure you guys are familiar with like GPT-3 and OpenAI's general way of just throwing more compute at a problem. And that's not really what happened here. Like, it wasn't just the case we took Alphafold 1, threw a bunch more compute and got Alphafold 2, or we took the previous winner at CASP and threw 200 GPUs at it and got Alphafold 1. What actually happened here was like, there's actually like a significant amount of innovation in the model itself, and the number of parameters are actually not substantially more than previous models like Alphafold 1 and Alphafold 2 have a similar order of magnitude on parameters. And it's kind of been quoted that it's about 6 to 7 solid ML papers of novel information, which is a lot of stuff. And so this entire model is not actually a whole neural network. The first, like most of it, is a neural network that's end-to-end optimized, and then at the very end, they have like a little bit of physics to just refine the model. And the physics is kind of just like, you have something that's not exactly right, and you have some forces, and you apply the force, and you end up with something that's like closer to the truth. And that's not really neural, but that is part of their model. And these are a subset, not all of them, but a subset of all the things that they use in the machine learning. I don't expect you to understand any of this stuff. This is just like a long list of things that people hadn't really used before together, and Alphafold 2 was the first one to do so. And hopefully by the end you'll understand it, like at least maybe like half of these, which is that's a success for me. And also I want this to be like a little interactive. Like there's a lot of things that maybe I'll skip over or I won't completely explain, and like please feel free to like be like, hey, what was that again, or what does that mean on that slide, or can you go over this again, or maybe I missed that. Like I want to hear these questions, and every couple of slides I'll try to pause and get this feedback because I want people to kind of understand. Cool. So the high level of what we're going to understand is like this diagram. If you look at the paper, maybe raise your hand if you like skimmed the Alphafold paper. the like 12-page thing online. Okay, cool. So the idea is that this is kind of the main image in the paper. And it's like a little complex. You have all these blocks. We're going to kind of break it down, and hopefully you'll understand basically what's going on here to go from our protein sequence in the beginning to our folding at the end. So the first thing in the beginning, that they have like this evolutionary model that I'll explain. And one might imagine that what Alphafold does is it just takes a sequence and in isolation puts it to a protein. That's not actually what's happening. It's actually matching it to a bunch of similar proteins, using all those sequences, and then using all the information from the evolutionary combination to make inferences. And we'll talk a little bit more about that. And all this part in the middle is the neural network part. And so that is kind of split into two parts. We have the Evoformer block, which is a neural network that maps all these proteins to a 1D embedding of one of these proteins. And the second neural network is it maps this 1D embedding to our 3D structure. And there's actually a ton of loops, like the Evoformer block keeps feeding into itself, the structure module keeps feeding into itself, and the entire network also feeds into itself. And this kind of works through like recycling, which I'll also explain later on in the presentation. Great, so we're going to kind of go through each of these steps in part. And at the end, I'll also give a little note on how exactly the force field is working. Great, so what is going on with this evolutionary model? So all these proteins look fairly similar, especially if you guys are at a distance. They're almost indistinguishable, but these are actually like 4 completely different proteins from 4 completely different animals. And like this protein and this protein look almost identical, but there's actually only 25% overlap in the amino acid sequence. And so this kind of gives us a hint for how we might use other proteins. And this idea of like multiple sequence alignment or using multiple sequences to get info about our original sequence is not new. It's been used in like the protein structure prediction problem for like a long time. But the two things to take away here is the idea of like a template and the idea of a pair representation. So a template is, let's say we want to get the structure for this protein and we only have the amino acid sequence. Then these would be templates that we refer to. And the pair representation would just be like a combination of these. And we like make some inferences with this pair representation. And so the paper refers to this jargon a lot. And so understanding exactly what these things are will really help you like dive into the paper and read it for yourself. Cool. So we're going to dig a little bit deeper into, okay, now that we have like 2 proteins that are somewhat similar, like how does this give us any information? Okay, so like our model doesn't exactly map like the sequence to the folding in isolation. Imagine that we have 2 similar proteins. And we know that because they're similar, similar amino acids have to be together, right? A protein is just a bunch of amino acids that we're trying to arrange in some like 3D structure. And if we know that 2 seconds are together, it's also the case that DNA kind of mutates in a way that nearby bases mutate like together. And so this gives us some information to, if we know that some base is mutated, then it's more likely that the bases near it in the human genome are mutated with it. And so that gives us a little bit of information that we can map from other proteins. And in addition, it allows us to kind of go back and forth, because if we know that these 2, for instance, are together, then we have a little bit of information, like the ones before and after it, and the ones before and after this one are also probably nearby. And we can kind of keep feeding that in. And now you can see where like the first feedback loop that we saw in the entire structure comes from, because we first, for instance, infer this, and then we infer things about these, and then we infer things about these, and so on. And so kind of get more and more accurate predictions over time. Great. Yes.
So it's clear that if you some sort of smell, probably do something better.
Yeah, so I'll kind of highlight exactly the models that are going backward with the message passing. But yes, this is kind of like, it's a little bit like message passing, that we're going from like a 1D representation to like a 2D like model that we can make some inferences from, and then updating the 1D representation and updating the 2D representation and so on back and forth. So it's not exactly message passing, but we'll go over what exactly it is. So specifically, like diving deeper a little bit into the actual technical details of this Evoformer block. So what is going on? So remember I told you we had our one-dimensional representation. So this is, we have all of our one-dimensional representations for each of our different organisms. So this is, let's say we want the human protein, then we want to make this top row into our protein. And here's a similar organisms, and this is our pair representation, which maps like an amino acid by amino acid grid. So let's say we have like 6 amino acids here. This would be a 6 by 6 grid that contains information about the pairwise distances between the amino acids. Right, so this is kind of the back and forth that I was talking about. This loop is repeated, I think, like 48 times in paper, and we can see that we get some information from the pair representation. We update the MSA. These are just various types of attention. The exact details are not that important. It's just some neural network manipulation with matrices. And then we update our pair representation given our update of the MSA, and we use something called triangle update, which I'll explain on the next slide. And the idea is that at the end, we come up with a new MSA representation, a new pair representation, which has kind of passed back and forth the information from the other organisms and our pairwise distances. Okay, any questions so far before I dive even deeper into this process? Yes.
So I understand why we're updating like anything. Like I thought you like have a bunch of like sequences and it's just like a line where you have like 2 sequences and you have like why exactly are we updating?
Right. Okay, that's a good question. So we've kind of already aligned the sequences with MSA representation, right? We know that like all these are roughly in the same place, all these are roughly in the same place. And so now the problem is, and like we kind of start with like maybe the original amino acid sequence, but like this MSA representation, it's not like the exact amino acids anymore. It becomes like an embedding of it almost. And an embedding meaning like kind of numbers to represent each one that we eventually manipulate further in the future. Right. So then we'd update that embedding, which would update like our guess distances for the amino acids in the protein we care about. Yes.
Just to check the dimensions of the sequence. So the top one has the number of similar proteins times the length of one protein, and the bottom one has the length of one protein squared.
Yep, one protein and one protein, exactly. And one might wonder like why is the pair representation useful? Well, because if we know the pairwise distances of all the atoms, we can kind of construct like a 3D model from that. Yes.
Why do we need multiple organisms?
Yeah, so it's kind of the thing that I was saying before, which is that we can actually get a lot of evolutionary information from the other organisms. Like if we know that some other protein folds in a certain way, and even if we don't have that specific folding information, the fact that we know that, say like let's say like this amino acid is preserved across all of these sequences, then we know that this one is like really important to the functional group and like doesn't change. But if we know that maybe some other one changes, we can infer, oh, like if this one changed, then like that DNA is next to like this other DNA, and so that one probably changed. And so there's just like a lot of like back and forth we can do here. Cool. Oh, right. Okay. So what is going on in that triangle update we saw? So the main thing that we want to ensure with the pair representation is that the triangle inequality is respected, right? Because we know that this is something that gives us some information about where different atoms are relative to other atoms. So for instance, the example here is, let's say we've inferred something about these 6 boxes. Then we've inferred something about the relationship between the 3 amino acids. And from that, we can ensure that we enforce the triangle representation. Now these are kind of just for visual purposes. You don't need to understand exactly what's happening here. But the idea is that we can use, for instance, knowing these 2 distances to infer this last distance or to bound it in some like range by the triangle inequality. And then once we've done that, it gives us a little bit of information about maybe even like neighboring ones, because we know that, for instance, if this is the closest one, maybe these have to be a little bit farther, and like the triangle inequality is also respected here. There's some other inferences we can make. And so again, kind of making this triangle inequality type of inferences again and again is how we kind of refine this pair modeling when we update it. Yes.
So like if let's say some distance wireless triangle.
Yeah. Right. So the idea is that it's just like plugging to attention. So we just have like attention blocks that we add like a triangle inequality constraint to all the attention. And so as a result, you can imagine that like we aren't like directly constraining it, but we're learning weights that maybe say like, oh, like if this is really big and that is really small, then we want to output something that's like kind of in the middle or something. And like then we assume the neural network will just learn like the types of relationships that it should constrain to. But we add like only the constraints of the triangle inequality, which is like should be less than the sum and greater than the difference. Does that answer your question?
So we do not have a strong guarantee that like triangle inequality will always be that you just kind of enforce it and we'll get.
Yep. Cool. Okay, so hopefully this is at least giving you some intuition for how we're doing this like back and forth update between like our original sequence and the pairwise distances. Great. And also, like, all these are affine transformations. They kind of refer to that a lot in the paper. Great. Okay, so hopefully this is giving you some intuition for like what the Evoformer block is and how we get to like our final embedding of our key protein we care about in the end. Okay, and now we can jump to the next part, which is the structure module. Great. So what is going on in the structure module? So remember, we have our one-dimensional embedding of the protein we care about, in this case, our human protein. We plug it through a bunch of stuff, and at the end we get like roughly what our protein looks like. And so we're going to kind of go through each of these blocks one by one. We're going to first start with like this big one that everything being fed into, and then we'll talk about these. So, okay, so what is this IPA module doing? And you can imagine each of these boxes is just like some sequence of like matrix multiplications, basically. It's just like a PyTorch block or something, where we take in some matrices and vectors, and we output some other matrices and vectors that maybe satisfy some properties. So it could be like an attention block, it could be like multiplication, it could be anything else. Cool, so focusing on this one. So invariant point attention. So the concepts we're going to try to go over here is like, what is invariance and what is equivariance? So the idea is that if we rotate a molecule, let's say we have like some property that we know is like pointing this way, like maybe there's an amino acid on this side of our like protein. And this is like kind of a simplified version of molecules. It's the same thing. And the idea is that if we want our input, if our input rotates, rotate this entire molecule this way, then we want to infer that the amino acid or the atom or whatever is like relative to this atom slash molecule slash protein in the same position. And so what this might look like is, let's say our neural network is like f of x, IPA, the IPA, like this whole thing is a neural network. Our rotation matrix is A and the input is x. So the input would be like our vector in this case. Then they kind of use the word invariance, like invariant point attention in like a little bit of a loose way. What is actually happening here is that like this is equivariant. And to go over the difference briefly, invariance means if we apply our neural network to a rotated version of the input versus the input, we get the same answer. So in this case, like let's say our arrow is pointing this way and we rotate our molecule, like in an invariant situation, where would our arrow be pointing? Same way, exactly. But in equivariance, the rotation is passing the entire network. So if it's pointing this way initially, it'll point this way at the end. Okay, so let's do a little quizzy quiz. So if we have a neural network that takes in the coordinates of two atoms, amino acids, whatever, two XYZ coordinates, 6 numbers total, and it outputs the L2 norm, the distance. Is this an invariant function or an equivariant function or both? Yes, it is invariant. Great. And if we take in two atoms, so again, our two coordinates, we output the cross product of the two atoms. So you know, kind of the vector at the end that's orthogonal to them. Is that invariant, equivariant, or both? Yeah, that's equivariant. And so you can see that by restricting ourselves to be invariant or equivariant, we restrict ourselves to like some class of vector and matrix operations. And only some of them are allowed. And as long as we use only those operations, no matter how we compose them, we can ensure these properties like invariance and equivariance. And this is how DMine has ensured that there's kind of no noise in the model from rotating the molecule or protein before or after the network. Great. So that was the IPA module. Then this outputs a bunch of information. So it takes in our representations and outputs rotations and translations for each amino acid relative to each neighboring amino acid. So remember with our sequence, we know like what amino acids are near other amino acids, but we don't know where they are relative to those positions in space. And so we output, you can see each of these little frames, and each of these frames represents an amino acid. The idea is we want to arrange them so that we, for instance, know this amino acid is south of this amino acid, and the next one is a little bit south of this. And so as long as we have these like relative transformations for each one relative to each other one, we can eventually reconstruct our molecule. And they call this thing called like residue gas. And it's a little strange of a name. I don't really understand why they call it gas. But the idea is that once we have these like relative transformations and we have some of them, you can still, so here, the example that they show is that, I don't know how well you guys can see, but you can see like our backbone frame or the location of some amino acids and some other amino acids that are coming out of it. And you notice that some of these are like fixed, right? And the reason is that we have enough information constraining the rotation. Let's say we know like this one is rotated at some angle and is at some coordinate, then we can exactly constrain the location of that from the original amino acid, but there's still some that we don't have enough information to constrain. So that is where this logic comes in, where we can't exactly reconstruct it, but by giving the rotation and translation of an amino acid relative to other amino acids, we can do much better than directly predicting the 3D structure, because now we can use computational methods and check if some positions are fixed and some are not. And this is how we're going to go from the output of our invariant extension to the actual 3D structure. Yes.
Wait, so how does it determine which ones can be computed exactly?
Yeah. Yeah, it's a good question. So there's it turns out that if we know, we can just write some inequalities on some of the parameters and say if all these inequalities hold, then we know that we can exactly compute where it is relative to the other ones. And so they just kind of have this code file. Yes.
Is the relative rotation and translation for every pair or for every one?
I believe it's just for each amino acid, and they apply it, and it's relative to the previous one and the next one. Yeah. But it's some output for each amino acid. Cool. Great. Okay. So now we've understood a lot of why we need this evolutionary stuff and how we find it. Right? We do we have our search over so kind of reviewing the whole thing. We search over all the other amino acid sequences, find ones that have similar functionality, and we take or similar shape, and we take their sequences as templates or pair embeddings. We feed them into this back and forth between our one-dimensional embedding of the protein we care about, as well as the one-dimensional embeddings of all the other proteins that are templates, and our two-dimensional pairwise residue. We go back and forth again and again and again. So we refine them. We get our structure module, which takes our final 1D embedding and makes it into a 3D structure. And we feed this whole thing back through. And so in the last step, they have the physics simulations. And it turns out that nowhere in what I explained did I say we constrain atoms to not overlap with each other. So what they do is they actually don't care at all about atoms being in the exact same position over time. And this allows them to iteratively refine and move around the protein so that even without that constraint, we can reach the final correct configuration. So here's a video of the animation. And you can see that we're kind of lines are going through other lines if you kind of look closely, and the protein is changing shape, and we're not really caring too much about that. And only at the very, very end do we kind of make sure with the force fields look there's no atom too close to some other atom. Cool. And so at the bottom, you see this is saying recycling iteration. And so basically what that's saying is that at the end of our entire network, we output some structure, but that structure gives us some information, right? We have some high confidence in some areas, some low confidence in some areas, and we can feed that entire thing back through the Alphafold network and recycle all the information we just found and go through all the weights and networks again, except with what we just learned. And this allows us with just some small number of weights to keep using them again and again and again, and refining them again and again and again, and getting way more power out of iterating over what we think our structure should be. Yes?
In what sense is it recycled? I get this, the backbone from the last step. It doesn't seem to belong at the MSA step. It doesn't seem to belong at the sequence to the structure steps. So where exactly is
Yep. Good question. So this is a pairwise distance matrix. So remember, we started with an empty prior over what we thought our pairwise distance matrix was. Then from this, we can compute a new pairwise distance matrix between each pair of amino acids. And now we have some prior of what we think it is. We also have confidence numbers. We just plug that back in to the original one, and we go through the whole process again. We kind of keep iterating again and again and again. Cool. Yes.
The confidence scores, are those calculated by physical plausibility, or are they some output of the network itself?
Mm-hmm. Yeah. So, it's a good question. I think it's not. I'm not 100% sure exactly how they're computing the confidence scores, but for instance, their loss function is very similar to an RMSD, but they have an additional thing that makes sure that we're not reflecting the whole molecule. But it's kind of similar to the RMSD from our reference, what we know the ground truth is. Yeah. So the network I don't think we never pass an array of confidences or anything. I think it's just that one can kind of intuitively imagine that the low confidence scores like our network will learn to detect them and like fix them. So areas where like the RMSD is like maybe the highest, they'll be like, oh, we like really need to fix this. And then we'll train to like, okay, work on like those areas a little bit more. And so we'll kind of like be able to detect like in the network itself, like where those regions are. Cool. Okay. Oh. Okay, great. So now we're going to talk about like I like threw a bunch of stuff at you and like all the different techniques they use, like what like actually matters. And so what they did is they did like an ablation study and they removed one of these like little components at a time, and then they determined, okay, like how does our model actually do? And so let me explain like what these graphs are. So the deviation on this x-axis is like how our new model without like whatever it says we're leaving out compares to the original model. So like on top does a little bit better, and below does a little bit worse. And similarity to MSAs on X. So on this x-axis, we're checking like how much information, how much overlap do we actually have with like the multiple sequence alignment. Remember back here I said like we get the evolutionary similar proteins, like the multiple sequences that we align, multiple sequence alignment. So how similar are those actually to our reference proteins? And so we can see that like at say like low similarity, we like don't actually, it's kind of a pretty new protein. We don't have too many similar proteins and we need to break the structure. Whereas at the end, we have like a ton of really good reference models. And so we see that kind of at the end, like it doesn't really matter whether we include or don't include any of these things, it kind of does the same. And that is expected because we already have the answers for a very similar protein. We can basically just copy that and learn how to do that. But the interesting stuff is what's happening like in the beginning, where we're trying to find newer proteins or more novel ones. And so we'll kind of go over like the important ones. So remember I talked about the IPA block, the equivariance and invariance. Turns out if we remove that and keep the entire rest of the network, it's exactly the same. And like it doesn't really change. And if we remove recycling, remember the looping back into the entire network, it gets worse. Kind of in the beginning, and here we have new amounts of information. But if we remove IPA and recycling, we like really suffer in the beginning. And that's kind of like an interesting result, I think, because that means that like it's something to do with like the combination of like these equivariant operations and like running it back to the network that actually has like a pretty big impact, even though the IPA itself is not doing anything. Some other interesting stuff, masked MSA head. So what is happening? Remember in the multiple sequence alignment where we had our different sequences. So if you guys are familiar at all with how NLP models are trained, for instance, BERT, what it does is that you remove a word and you try to guess what that removed word was. And so we do the exact same thing here as part of our training steps, where we remove an amino acid in the protein and we try to predict what the amino acid that we removed was. We like slightly change like our prediction problem. And we kind of feed that back to the network. That's like our masked MSA head. And it turns out that if we add this like extra step, it actually does quite well. And if we remove it, it is like really badly when we don't have like a ton of information about the protein. So that's also interesting that this like kind of very NLP inspired sentence thing is quite important. What else is interesting? Self-distillation training. This is like an interesting thing. Are people, raise your hand if you're familiar with self-distillation. Cool, okay, so the idea behind self-distillation, raise your hand if you're familiar with ensembles. A little bit more, right? Okay, so ensemble is just if we have like many neural networks that are exactly the same and we train them all from different random initializations, the idea is at the end, all of our neural networks will have like learn slightly different weights. But if we just average all the outputs of all those different networks, we'll get like a result that's better than each of them individually. And so self-distillation just says, okay, now what if we trained like a final network, not on like the actual answer we're looking for, but on like the confidence scores outputted by like our original model. So we, for instance, like this is very inspired by like image models where like you output like, 90% probability is a dog, 5% is a cat, like 5% is something else. And we train on that instead of 100% probability is a dog. And it turns out if we do that, our model like really improves because now we have way less parameters. We don't have to train like, X number of models at once. And we're training on like what exactly our output should have been in terms of the probability world and not like the kind of, deterministic, we want it to be this like one thing. And so this type of training is quite helpful. And we see that like without this type of self-distillation, we do quite poorly again when we don't know a lot of information. Cool. Right. So we kind of discussed the masking and the self-distillation. Great. And so if you guys are interested in kind of learning more, I'm going to go back a little bit and we're going to talk a little more about kind of the specific, all the things I brought up in the first slide. But if you guys are interested in learning more, there's 2 really well-written blog posts. This one is fantastic. It's like Bilal Farashi, and she has like a really solid explanation of kind of what is going on, like quite intuitively. And this other blog is also quite good. And you notice that if you guys read the 12-page summary, you actually like get very high-level information and know like actual details on how to implement it. And then all the actual code and the details is like in this like 62-page like behemoth of a supplement, which is like probably why it took them like months and months to write this thing up. And like this one is pretty tough to get through, but like I think the blog posts do a great job of summarizing what they talk about. Right. Okay. Cool. So I'm going to go back a little bit into our original slide where I brought up all the things that, or some subset of the things that this model uses. Cool. So we talked about self-distillation, self-supervision was kind of the okay. So basically, what's happening with that step is we know like a bunch of like labeled protein data, right? We know that like this is the mapping of like this sequence in this animal to like this protein. We also have a lot of like unlabeled protein data, and it turns out that like we can actually use this data by just like throwing it into the network and putting it into the loop so that we additionally use those in the prediction. And this is kind of like the self-supervision prediction. If you guys remember self-supervision, we use like the unlabeled data in addition to your labeled data, and you get a more accurate prediction. Yes.
Because you said the self-supervision is just masking out like certain amino acids or reconstructing it. Does that mean like the self-supervision only applies to like the first part where you're getting the embedding of the amino acid? Like the second part of the network that predicts the structure, it doesn't have like an equivalent type of self-supervision, right?
I'm not 100% sure where exactly happens in the network, but like that seems like a reasonable thing to me. I think they discussed it exactly. If you look at like the given supplement, we can look at it like after the talk and just double check. Cool. The new loss function. So they use something called FAPE. So this is kind of at the very end when they're checking it with like a reference position. And it's like, and the idea is that you guys know like RMSD. Raise your hand if you know what RMSD is. Cool. So it's basically root mean square distance. The idea is that we want to, it's kind of, you can imagine it being like, let's say like our real amino acid is here and our prediction is here. It's just like the distance between those for each like amino acid. You can like think of that as like a reasonable approximation. And then we root mean squared. So we square them all, take the mean, and take the square root of all that. And that gives us like our number. But there's this interesting property of molecules and proteins called like chirality. And you can imagine that if we like flip this molecule, like reflect it exactly on like, and just like flip the entire thing. There's no way, like we just like bury it on like some plane. Like there's no way to like rotate it and get back to that like non-reflected state. And so we actually want to enforce this additional thing in our loss that like we have the correct chirality. So we're not like the mirror image, because the mirror image you can imagine might actually have like a low loss, but in reality, like this chiral molecule, this like reflected molecule is like meaningless. It doesn't actually exist. Yes.
Because you can superimpose them, wouldn't that be reflected in the loss?
Right. Yeah. Exactly. Because you can't rotate it to the same position.
So why do you have to do anything else?
Yeah. I mean, so let me think. I think it has to do with like how exactly we're doing the distances relative to each other. Like if you imagine like, let's say like we're analyzing like pairwise like these two amino acids away from each other, then like their RMSD would be exactly consistent through the entire molecule, but like it might be like a mirror reflection of like the actual molecule. So it probably has to do with like the losses that they're computing with like multiple amino acids. Right. Okay. Cool. So that's their kind of new loss function, and you can look at the exact equation in the paper if you want. And then to redo refinement. Right. So at the end, we saw we wanted to the force field. That's kind of the 3D refinement to do the last step. Recycling after the refinement. So you can do recycling on like the entire network. So remember we refine it, we get our new like 2D distances, and we plug them in back to the entire network. Refinement after recycling, you saw like the inside. Like here, we like recycle in these modules as well before we like send it to be refined. That is refinement after recycling. After variance, I explained to you guys we like use some subset of functions on the back of the matrices. Templates, right, where the similar sequences. Full MSAs, we use like full sequences. To tide weights, this is like, the idea is you can slightly reduce weights by like combining like your softmax with like the actual operation you're doing. It's just like a hack to like reduce some weights. And so they have some of those, don't have some of those. And then attention over everything. So, oops. Right. So if you notice kind of all the blocks in the, like when I went a little bit deeper into each of these parts, they were doing attention on like a lot of things. There's like attention on like the nose, the edges, the coordinates, and this is like really like, I mean, they're just like throwing like tens and tens of attention blocks of like different types into the model. And so that was also a pretty interesting innovation. Cool. Yes.
Yeah, on the like the IPA, the weight invariance
Yes.
part, is it just that like attention is naturally like rotation invariant, or is it like something specific to the weights that makes them like?
Well, I think the idea is that you can do like additional things. That you can do like things like dot products. And if you just think about like what a dot product does, like it, maps like two vectors to like something on the first vector, like that kind of like, you can think about that like is equivariant, right? We can rotate the original two ones and we can use that as well. So now you can like, instead of just attention with like multiplication and addition, you can also throw in like a dot product. And so it just kind of gives them a little bit more flexibility in the types of things they can use and like ensure that they have like this property, which is like the main thing we want to make sure.
The last question. For this IP thing, you said that when they took it out, it actually didn't do that for you. What would explain such a thing? I would have expected like a priori that this is like critical of making sure that like they're not like out of sync and just like.
Yeah, it's a good question. So I should have been a little bit more clear. It's not that they're like removing it and putting in something that's like not invariant equivariant. They just like remove the additional power that like these additional functions use. So they take out like whatever the dot products, all this like additional stuff, and they just use like pure attention. Like pure attention is as you mentioned, like, invariant equivariant, because it's just a multiplication and addition. But you like lose all the additional power of like all the additional operations that we can add. And so they just remove like all the additional stuff. Yes. Yeah. I mean. Right.
So the two kinds of recycling, the internal one is just like iterated application of one thing.
I believe so, yeah.
And then the external one, the external one sounds like the whole thing is being iterated somehow. What part of the output is getting fed back in as input to the next iteration?
Yeah, I think it's specifically like they take like our final structure and they compute the pairwise distances. And then when we start with this like guess over all of our pairwise distances, like we think these two amino acids are like this far apart. Like we imagine like this randomly, we start this like randomly initialized, but we can start to initialize like whatever this output is after all the force field stuff, after we like do all the changes, and then we feed it back to this. And now we have like a better prior over what this is. And so we run all of this again and keep refining like this. Because now we have like, for instance, we can take our like structure here and like add the evolutionary information, right? And the force field had no access to evolutionary information, but we can like basically say like, look, we applied the force field and now we can add like some more evolutionary stuff, make this more inferences we can make, right? Maybe after like doing this force field stuff, we like some new two amino acids are next to each other. And like, some other animal, like those two are next to each other in like a different way or a similar way. Like make some inferences based off of that.
So in some part, the core thing that's going on here is yes, it will pairwise this instance. And you do this many times, and then you do like a force field, and then you go back and you get like new evolutionary information, and then you take like another 48 passes at guessing.
Or I think the 48 is like internal, like this specific loop is repeats 48 times, and this whole like big recycling loop is repeated only 3 times, I think.
Yeah. Okay. Gotcha.
Yes. So training was done with 200 GPUs. So if you're an employee at Google, that's easy. But for anyone else, it's a little tough. Inference. Yeah, just like running inference. Yeah, they have published the weights on GitHub. If you run inference, I don't know how long exactly, but inference is generally fast, so I wouldn't expect it to take like that long. I think it's like these, like you could probably run it on your laptop, just like throw in some protein and try to do some inference. I think you could probably do it. Yeah, so the standard is the physics simulator standard software. It's called Amber. Yeah.
Link to the 62-page paper.
Yeah. And we can look at that. Cool. Yeah, so this is really the yes. Yes, is there a specific thing you want to see? Oh, the URL. I'll share the slides to the calendar event. If you guys, yeah.
The slides, so we'll probably post all like the slides and like the paper for the reading work on the website for you. That's gonna be updated soon. So
yeah.
We'll like send an email and it's like all up there. We plan on doing it every week to like put the paper and whatever slides we present on the website, so you guys have it, and I'll centralize those. So yeah, it'll be up soon.
Yep. And if you're not part of the AI at MIT mailing list, definitely join that. Yeah.
Maybe like one last question for me is like I just spent my time with ML, so I don't know anything about like the bio or like this side of things. How like popular is it becoming in like these types of problems to actually be using like state of the art like deep learning techniques and stuff? Is that like just like a deep thing, or is this actually more practical?
Yeah, it's a good question. I think it's actually quite prevalent. Like if you look at like the vast majority of papers coming out nowadays related to like computational chemistry, and even before the DeepMind papers, they were using neural methods. Like attention would come out and people start using attention, and so it's. I think there's kind of this perception that like a lot of biology and chemistry is like behind the rest of ML, and I think like these days, like looking at the papers, like for instance, I was doing a bunch of research on like equivariant networks this summer, and like there's I think there's a good amount of like basically all the relevant chem models these days are using like attention and newer things from literature. Yeah. Yeah. If there's any like specific question about like the nitty gritty, we can also like scroll through the supplement and try to answer those. Yeah.
How do you actually implement like
Yeah. Yeah. That's a good question. So the constraint is enforced, the equivariance constraint is enforced because you only use a couple of functions, right? So you can imagine that like no matter how you compose a bunch of dot products, like they'll be equivariant because like the f of xa, the f of ax, you can keep factoring out the a from all the f's. And so kind of by definition it is it is equivariant, but we can kind of see like the full like all the different things that they're using in the IPA. You can see that they kind of here's like the dot products I was talking about. If you want to, there's like various tensions that are happening. They're also equivariants. There's linear. There's matrix multiplications that are equivariant. You're just multiplying by scalars. Yeah, good question. Yeah, anyone else want to dig a little deeper? We can also just kind of wrap it up, and then people who want to talk more can stay. Cool. All right. Thank you for coming.
So we don't have, I'm pretty sure it's not good for everybody. And also we promised some people later, we're sorry to work out. So we're probably gonna take it like out, so you guys can like grab it and eat outside, like talk with each other. It's like we don't have plates, so you guys will leave them. Anyways, so if you're not able to have food, like it runs out, please like get food for yourself. We were saying totally like don't go like some like 5 stars on like some of like a $200 bill. But like keep it like a Chipotle burrito is probably good, and then just send us like an RFP and like reimburse you. But the only thing is like you have to make sure it fills out a tennis form so I can actually prove here, so you don't just go get a bunch of RFPs to like random people. And then the attendance form, I think it was up at the beginning. I'll put it up.
Yeah, I can throw back up that QR code.
So like I think the plan is if we take it out, like in front of Saba, you guys can just like enjoy it outside and like talk amongst yourselves and leave. But if it runs out and you're obviously getting any food, just make sure your name is on the attendance list. And also try to get food first. Don't like all leave and then send us our like I'll make sure you get what we have, but if you want to get it. on that QR code, there's like it should lead you to like 4 links. There's also a presenter interest group. If you're interested in presenting, we'd love to have
Yeah,
you.
please present, like, the
Yeah.
only way this one happens is if people present, so.
Yeah, so please fill that out. We like it's super chill as you see. Like you just come in, it's like it's fun. And then also if you're interested in being on board, which is basically if you help out with like reading groups, different initiatives, it's super fun. You get to help play with Zach and I. Like that's also really fun. So if you guys are interested in that, there's also like another form on there. But yeah, so I think it's nice to take this out, and then you guys can like follow us and we'll all go.
I want to say one really quick thing. Like this paper is nothing like something that, so you're sort of good on all like well, there's like
Yep, yeah, that's a great point. Yeah, and feel free discussing less complex papers, like you're like, you know, you're doing something in your Europe and you want to present, like we'd love to have that. Yeah, do you want to just hear? Okay, yes, stop.
I'm really curious about this specific here. The type of this paper.
Go ahead.
Oh, no.
Go ahead.
I mean, I can just quickly answer yours and then. Yeah.
Really, I'd say I'm taking this to be.
Okay, yeah. You want
So you're familiar with that? Well,
Yeah.
do you read the paper? I haven't read it.
I haven't read it. So here's what I know about Rosetta Fold. Like, I believe they looked at basically what Alphafold presented during CASP, and they looked at like their really brief. It's supposed like a 1-page thing or something like after CASP, and I think they just tried to reconstruct the whole thing from that. And they missed a lot of key stuff, obviously, because like all the details are public. They were like, they missed some notes, whatever.
But is that comparable?
Yeah.
Actually, and they like read. It's apparently like pretty different architecture.
Yeah, I mean, because they were going off of like very wrong information, right?
Yeah, that's why I think it's interesting that they still got.
Yeah. I mean, so like it does bring up a good question. Like, to what extent, like what things do matter and what things don't, right? And one can say that like because of something like Rosetta Fold works, it's probably the case that like the number of layers and like the order of them doesn't matter that much. It just maybe matters like, oh, we have these types of layers, or like, you know, we do recycling. Like, the exact details are not that relevant, which is why I didn't spend that much time on them, because it really seemed that like, you know, you can kind of compose any of these things in whatever way you want, as long as you have sufficient number like weights. Yeah. You want to?
Wondering, I read the article about the derivation of the gradient for physics simulator a year ago, so
Of the gradient of the potential.
yes. My recollection's not perfect. And then if I remember, they find a zero Schley energy at one point along the conformational structure, and then used its positive definiteness to try and optimize the global minimum. I don't think that's. They didn't use an iterative method, so it wasn't be positive definite, otherwise they would put at least squares.
Right.
Oh, are we on camera?
Oh yeah. Let me turn that off. Sorry. Forgot about that. Let's stop share. Let me